All right, so we've talked about graphing sine and cosine and the big kind of takeaways we should have. When we graph y equals sine x, we are starting at our equilibrium value, going up to our max and our minimum, and then back to equilibrium in 2 pi radians with a max of 1 and a minimum -1. When we do cosine, sine and cosine are really expressing virtually the same relationship, just at a different period along the wave. So instead of starting at equilibrium like sine does, cosine starts at its peak and goes through its oscillation, also in 2 pi radians, still to a max of 1 and a minimum of -1. It just starts and stops in a different location. If we continued this wave, we'd see they are essentially the same shape, just at different points within the wavelength. So all the rules that we have for graphing sine in terms of compression and phase shift and amplitude, they're all the same, which makes graphing sine and cosine, once you know how to do one, knowing how to do the other one generally comes pretty quickly. Tangent can be a little bit different of an animal. And I want to talk really quickly, before we look at the graph, about some physical representation of what tangent is. I don't know why I felt compelled to try to draw a circle. I can do that and then move it. Okay. So when we think about an angle coming out here, or a ray coming out here, making our angle in standard position, we quite rightly conceptualize our sine value as the length of this edge, or if you prefer, the kind of vertical displacement up from the axis. We conceptualize cosine as this length, the kind of horizontal displacement caused by that angle. And when we're talking in terms of triangles, we talk about those as being the opposite and adjacent sides, respectively, or the x and y coordinates of that point up there. Some x, y coordinates. The x value was, of course, our cosine, and the y value we associate with our sine, as long as our radius was 1. If our radius wasn't 1, we just divide out the radius, and we still get our sine and cosine values. Now, when we found tangent, the tangent was supposed to be the ratio between opposites and adjacents. It's supposed to be the ratio between the y's and the x's. But there is another physical interpretation of tangent that actually kind of gets to the point of why it's called tangent to begin with. If you recall your definition of what it means to be a tangent line hits a curve in one location, in one spot. So if we made a line tangent to the curve at this point, so that's still perpendicular to that axis. So a line tangent right there, this length is actually the tangent value for that angle. So if that's angle theta, this length is the tangent of theta. It's the length of the line tangent to the circle that makes that connection. And you could verify this by drawing them out and finding that ratio in similar triangles, move that ratio over. You know, if you consider this to be R and that R plus. But it does give us a nice physical representation for that tangent, and frankly, why it's called the tangent, because it's the length of that line tangent to the circle, perpendicular at that point. Similarly, this length here, this orange length up until that point, that orange length is the physical representation of the secant value. The secant of that value. Secant comes from the Latin to cut. It's the line that, or the ray that cuts through the circle. So it's that length up into where it hits that. So we've got our three main functions here. This angle causes a sine value. That's that green one. It causes a tangent value, this purple one, and it causes a secant value, this big orange one, are really the three values caused by that angle. And you might say, well, what about the cosine? Where's the cosine fit in? Well, you remember the cosine, cosecant, and cotangent, those are all functions talking about the complementary angle. So if we imagine this little complementary angle here, I'm going to call it phi, just to call it something. We could make a similar argument about sine, tangent, and secant from this other angle. Just our sine would be here instead. Well, notice that dark green sine of phi is the cosine value. It's the same as this x value, that cosine of theta. So that's your cosine value. Similarly, if we went tangent at this point, that length from there to there, that's your cotangent value. And from there down is your cosecant value. So all those cosine, cosecant, and cotangent values are just the sine, secant, and tangent of our complementary angle, hence the cosine, cotangent, and cosecant. So, if you ever wondered where these names came from, that's a little blurb for where those names all came from. But I really want to focus on that tangent. So again, one of the ways to visualize what the tangent value is, yeah, we could just calculate the ratio between y and x as we go along the circle. But if we want to look at what the graph is, it's actually kind of handy to look at that physical representation. So for example, if I've got my circle here and I force this to go through an angle, you notice that this length here, that 1.88, if we figured out what the coordinates of this point P were and took the y divided by the x, notice it's higher, so the y would be larger than the x, so its ratio would be bigger than 1. This value is bigger than 1, but it is the physical length of that red line is our tangent value for a 62-degree angle. We remember that the tangent of 45 was supposed to be 1. Let's see if I can put this at 45. I can't quite make it go 45. But we could imagine if it was 45 degrees, this length here of 1 should match that length of 1. So it should be that height. So hopefully it seems reasonable. And if we look at what those values do as we go through our angles, we make a nice graph kind of build itself as we go through. So as we look at increasing that value, you'll notice the tangent values start getting quite large. The 4.33 might not seem very large, but remember, sine and cosine maxed out at 1. So it's already quite a bit larger than sine or cosine could ever have been. If we go, whoops, I shouldn't have done that yet. If we get into the 80s, we can't even see it yet. We could try to change the scale and look at it. But you can imagine the length of that red line is going to be huge. It's going to hit up here somewhere. If we try to go even a little further, I want to stay under 90. Ooh, that's a good one, 88. The tangent of 88 degrees is a very large number. Let's figure out what it is for the fun of it. Tangent of 88. And I want to make sure that's degrees. Tangent of 80 degrees is almost 30. Okay. So that length is getting to be almost 30. And we could keep going and try to get pretty close to 90. But if you try to imagine what would happen at 90, that ray is going straight up. So how long is it going to be until that line going straight up hits this tangent there? How long is that going to have to go? Well, at 90 degrees, those are never going to intersect. So at 90 degrees, and again, if I can get this thing to sit at exactly 90 degrees, I'll be lucky. No, I can't do it. But anyway, if we got it to sit at 90 degrees, it wouldn't have any value. It's undefined at 90 degrees or at pi over 2 radians. Okay, what happens if we keep going? Well, if we keep going, okay, it's not going to hit as we go forward this way, but if we let that ray be a line, as that line turns past 90 degrees, that line still intersects the line tangent to the circle. It just intersects it way down on the other side. It intersects it down there. And we know in quadrant 2, our tangent should be negative because our y's are positive and our x's are negative. So we get these nice negative values heading back toward 0 at pi. So this kind of, couple of sweeps asymptotic at 90 degrees or asymptotic at pi over 2 radians is our classic behavior of tangent. If we kept going, notice it starts to go through those same values again. It starts to recreate that first blue curve. And if we keep going, it will continue to recreate that first blue curve. The values in quadrant 3 match exactly the values in quadrant 1. From the perspective of where does this intersect, the difference between the ray being up here and the ray being down here, there's no difference between those things. Same values. If we keep going, we'd get at 270 degrees or 3 pi over 2 radians. We'd hit an undefined point again. Ooh, that's really close. We'd try to hit some undefined point way, way up there, or try to get infinitely large, and then those two lines would become parallel and they wouldn't intersect. And you can hopefully imagine as we go down here into quadrant 4, we're negative again, and we're back down here. So these kind of big, some people say snake-like, but these big curves going up with these asymptotes in between them is our classic behavior for our tangent function. Now, this is what the graph looks like between 0 and 360 degrees. So if we took that and tried to look at, okay, what's it going to look like if we graph it between 0 and 2 pi, it would, like that graph did, start increasing until it reached pi over 2 radians. And then it would come up and be asymptotic again at 3 pi over 2, and then come up again stop at 2 pi. So if we chose to graph it from 0 to 2 pi, that's the graph that we would end up looking at. Now, why would we graph it from 0 to 2 pi? Well, that's where we graph sine and cosine. So that should seem at least somewhat reasonable. But it's actually more convenient for tangent to look at its graph. There it is. Look at its graph instead of from 0 to 2 pi. Look at its graph centered about the origin, or centered around the y-axis. We know it goes from there upward, asymptotic to pi over 2. But if we look back this way, those negative angles, those small negative angles are down here in quadrant 1, giving us negative tangent angles. So we're going to have that downward sweep going into those negative angles. So essentially, this sweep also happens down there and has that asymptote at negative pi over 2, or negative 90 degrees. So this gives us actually a full picture of what tangent does in only 1 pi radians. It starts to repeat itself every 1 pi. If you go out another 1 pi in this direction to 3 pi over 2, that sweep is repeated. You go back to negative 3 pi over 2, again, a distance of pi radians. That sweep is going to be there again. This is one of the major differences between sine, cosine, and tangent. Sine and cosine, they have to go through the full rotation, the full 2 pi radians, before they start to repeat themselves. Even cosine has to go through its full oscillation from 0 to 2 pi before it repeats itself again. Because of the nature of tangent, and essentially because it can't tell what quadrant it's in, whether it's in, when it's over here, it's positive. When it's down here, it's positive. Tangent thinks those 2 quadrants are basically the same. So it maps on top of itself. So it has a period of only 1 pi radians. That's going to be actually pretty handy later on. Well, it's also going to be kind of troublesome later on. So it has benefits and weaknesses. So if we're trying to graph tangent, say, for example, we're trying to graph the tangent of 3x, we know that that 3 is supposed to reduce our period. If this was sine or cosine, we'd take our period, 2 pi, and divide by 3. But this is tangent. And we know from what we've done over here that this natural period for tangent is only 1 pi. So then when we divide that by our 3, by our compression factor, we're going to get a period of just pi over 3. So if we tried to draw that, it's going to be, again, centered at our origin. Going to go up from there, down from there, such that the distance between our asymptotes is pi over 3. Which means this point is actually only going to be at pi over 6. Half of it in that direction and half of it in this direction. That's going to be at pi over 6. That's going to be at negative pi over 6, making that total period the pi over 3. It's one of the easy mistakes to make, is to try to go that full pi over 3 in both directions. But then if you wanted to know where the next asymptote is, you'd take that pi over 6, add your period. Pi over 6 plus pi over 3 is pi over 2. And you've got another sweep. Where's this point? Well, this point was at 0, add pi over 3, that point's at pi over 3. The next time that point occurs had better be at another pi over 3, so 2 pi over 3. And we could draw as many periods of tangent as we want. So really our compression factor and our phase shifts and our lifts, all of that will work exactly the same way for tangent as they do for sine and cosine, with the one difference that the natural period for tangent is only 1 pi instead of 2 pi. That's really the only difference. And of course it has these asymptotes in it and whatnot. So if we want to get complicated, I don't want this video to be too long, but if we tried to get a little complicated and say, tried to graph the tangent of, what do I want to have here? How about pi over 4x minus, I don't know why that's saying control, that's weird. Still doing it. That's why. Sorry, pi over 4x minus, let's say, pi over 2, why not? Plus 1. And we wanted to graph that. Sure, we could have a computer graph it for us, but it's nice for us to learn how to find these values nice and exactly. We've got a couple things happening here. One, instead of having our middle equilibrium point be at y equals 0, this lift is going to pull us up positive 1. We have an amplitude of 1, but amplitude really doesn't mean as much for tangent as it did for sine and cosine, because there's no limit top and bottom. We're just going to scream all the way up towards infinity. So I'm going to kind of ignore that amplitude. This value is going to tell us about our phase shift, but we have to be a little careful. Our phase shift isn't pi over 2. We have to remember to divide out this compression factor. Now we can either do that by going over and deciding that our phase shift is that C value divided by the B, divided by that compression factor. So that's pi over 2 divided by pi over 4, which is just equal to 2. Or we can go up here and factor out that pi over 4 if you like having it in this form. Just depends on what your preference is. Or go off and divide it and then write it in that form. Whatever makes you happy. So that gives us our phase shift of 2. So I'm going to go over 1, 2. So that's where the center of that sweep is going to be. But where are our asymptotes going to be? So I know we're going to come off of that in that classic tangent sweep. It almost looks like a x to the third polynomial. It's not quite. It's different in shape, but it's very similar. So if we want to find our period, we find our period by taking our natural period and dividing by our compression factor. Just our natural period this time is pi instead of 2 pi. So pi divided by pi over 4 is equal to 4. So the entire length of our period is going to be 4. So from this value at 2, if we want that entire thing to have length 4, we got to go 2 back and 2 forward. So we're going to have an asymptote there at 4, an asymptote at x equals 0. We'd have another one at 8, another center point at 6, and we could draw in our sweeps. And we could repeat that and draw as many as we wanted. Now, if we wanted to figure out exactly where it crosses there, we could, and we'll talk about that if you want to. That amplitude does affect where those quarter points are. So, instead of having a max at that quarter point, this quarter point is going to be off by the amplitude in value. So we really actually will go through that 0.10. That's not terribly pivotal for us, but there is an interpretation of that amplitude. If this amplitude was, say, 5, then this thing, instead of going down 1, would go down 1, 2, 3, 4, 5, and would be stretched way out down there instead. But that's not what we were graphing. And I'm not going to ask you to make those distinctions for your tangent graphs at this stage in your career. So using those same ideas that we use for sine and cosine, we can graph tangent. So play around with that. If you have any problems with it, let me know.